Welcome to this college algebra video on graphs of inverse power functions and rational functions. So just to quickly remind you what a rational function is, a rational function is a function in the form n of x over d of x, where n of x, or the numerator of that fraction, and d of x, the denominator of that fraction, are both polynomials, and d of x is not the zero polynomial. One of the critical concepts on rational functions is the domain of a rational function, and the domain is all real numbers that do not make the denominator equal 0. We want to avoid any values of x which would cause the denominator of a rational function to equal 0. So just to see if you are understanding that concept, why don't you see if you can find the domain of each of these functions. You can pause the video and try these problems yourself, and then I will come back in just a minute with the solutions. Let's start with little f of x. You should notice that the denominator is x minus 1, and the value that would make that denominator equal 0 is a positive 1. So we say the domain of this function is all real numbers except x equal to 1. So a short way to write that is x should not equal 1. Moving over here to g of x, we see the denominator is x squared plus 4. Well, if we try to make x squared plus 4 equal 0, there are no real numbers that would make x squared plus 4 equal 0. So the domain of this function is all real numbers. Moving on to little h of x, the denominator is x squared minus 6x minus 7. Now it's not immediately obvious what numbers would make this denominator equal 0. So hopefully you thought to factor x squared minus 6x minus 7. That factors as x, and 7 is 7 times 1. And to make sure we get a minus 6x in the middle, we need a minus 7 and a plus 1. And that means the values that make this denominator equal 0 are 7 and negative 1. So we do not want x to equal 7, and we do not want x to equal negative 1. Finally, for capital F of x, our denominator is x squared minus 3x plus 2. Again, we need to factor this denominator. It will factor as x times x at the beginning, 2 times 1 at the end, and this time both of them need to be negative to make the minus 3x in the middle. So we should not let x equal 2, and we should not let x equal 1. The domain is all real numbers except for 2 and 1. Now notice that throughout this entire process, I completely ignored the numerators. And as far as domain is concerned, the numerators have no part in this process. So let's switch over to the concept of graphing rational functions. And to begin with, we're going to graph the simplest kind of rational functions. That is a rational function where the numerator is simply a constant and the denominator is just x to some power. So a very simple polynomial in the denominator. And I'll be using Desmos to illustrate what these graphs look like. So we're starting here with the simplest of inverse functions, and that is the function 1 over x to the first power. So just 1 over x. If we take a look at a few different x values, at x equals 1, our value is 1 over 1. At x equals 2, our value is 1 over 2. At x equals 4, our value is 1 over 4. And then 1/5, 1/6, and so on. So these fractions get continuously smaller, closer and closer to 0 as we move out to the sides. As we move closer into 0, we're getting values like 1 over 1/2, which would equal 2, or 1 over 1/4, which would equal 4. And finally, we're here at 1 over 0, where there is no function value. 1 over 0 is undefined. We move to the negative values, we see values like 1 over negative 1, 1 over negative 2, 1 over negative 4. Again, these fractions getting smaller and smaller, approaching 0, but this time from the negative side. Let's just explore a little bit of what happens if we change the coefficient, that number in the numerator. So this is the function 1 over x. As we go to 2 over x, 3 over x, and so on, the shape stays the same, but the branches of this graph, that's what we call these. This is technically a hyperbola shape, and the branches of the hyperbola just move farther and farther away from the origin. If we get closer to 0 for that coefficient, like 0.6 over x, 0.4 over x, now the branches move closer and closer in to the origin. We finally hit 0 over x, that's a straight line. And as we move to the negative, notice what happens here. The branches have now switched corners. Instead of being in the first and third quadrant, they are now in the second and fourth quadrant. Again, as that coefficient, that numerator moves farther away from 0, the branches move farther away from the origin, and as we get closer to 0, the branches move closer to the origin. So let me reset this as 1 over x again. And let's try changing the power of x. So we see what 1 over x to the first looks like. What does 1 over x squared look like? Here's the graph of 1 over x squared. Notice that this time both branches have positive y values only. Well, that's because I'm dividing by an x squared. X squared can only produce positive values. I like to think of this thing as kind of an infinite volcano. It's the volcano graph, but it's an infinite volcano graph. And if I zoom out on this thing, you'll see that the farther out we go, the higher and higher this volcano goes. This volcano will never have a top. It's not a mountain because there is no value at x equals 0. So there's always going to be a tiny, tiny gap between these two sides of the graph. Let's see what changing that coefficient will do. So this is 1 over x squared. And as I move out towards 2 over x squared, 3 over x squared, and so on, you can see that the branches basically go farther and farther away from the origin. As we move closer to 0, these branches move closer into the origin. So in a sense, it's like those vertical stretches we've seen before on all graphs, and a vertical squash if we get close to 0. Right at 0 over x squared, of course, there we have a straight line. Every value equals 0. And let's see what happens if we go into the negative. So a negative number over x squared. Well, now we've got what I think of as like a bottomless pit. As we move farther and farther down into the negatives, this graph gets stretched farther and farther up. You can see those points at the values x equals 2 and -2 are just stretching further and further down. But this is basically a bottomless pit graph. Now we're back at the graph 1 over x squared. Let's see what 1 over x cubed looks like. There's 1 over x cubed. Looks very similar to the first graph we looked at, 1 over x, and our branches are in the two corners here. Let's go to 1 over x to the fourth. It's the infinite volcano graph again. 1 over x to the fifth. The branches are in opposite corners. 1 over x to the sixth. Volcano graph. And even with 1 over x to the sixth, we can either have a volcano graph when the coefficient is positive, or we can have a bottomless pit when the coefficient is negative. With 1 over x to the fifth, our branches are in the first quadrant and third quadrant. If we make our a value negative, the branches switch quadrants, now in the second quadrant and fourth quadrant. So let's summarize what we should take away from that exploration we just did. When we have an inverse power function, some real number a over x to some whole number power, when the coefficient a is greater than 0, we have two branches of a hyperbola, and they are in quadrants 1 and 3. When a is less than 0, that is a negative coefficient up here in the numerator, we get two branches of a hyperbola, this time in the second and fourth quadrant. And that a value, again, can stretch the graph or it can squash the graph down. A is bigger than 1 will stretch the graph farther and farther away from the origin. A is closer to 0 will push that graph closer and closer to the origin. And this is true for any odd degree inverse power function. That is when the power of x is 1 or 3 or 5 or 7 or so on. When we move on to a over x to an even power, a over x squared, a over x to the fourth, a over x to the sixth, and so on. Here's what we found. When the coefficient a is greater than 0, we have this infinite volcano graph. When a is less than 0 or a negative, we have this infinite bottomless pit graph. Now, if you're looking for a way to remember which quadrants these branches are in and what these graphs look like, I'll remind you that for an odd degree polynomial function, what we saw was a swoosh that came up from the third quadrant and went up into the first quadrant when a was positive. When a was negative, we saw a swoosh that started in the second quadrant, came down through the origin, and went down through the fourth quadrant. So if you can remember what polynomials do, it will give you a hint as to which quadrants your branches of your hyperbola should be in. And likewise, when we had an even degree polynomial with a positive, like x squared, x to the fourth, x to the sixth, and so on, we had a u shape that pointed upward. And when we had an even degree polynomial, like x to the fourth, x to the sixth, but a negative coefficient, negative x to the fourth, negative x to the sixth, we had a u shape that pointed downward. So again, where this graph is, shows you the two quadrants where your branches of the hyperbola should be. It's almost as though the inverse power functions are polynomial functions that have been turned inside out. Now, when we talked about polynomial functions, I showed you some dance moves that you could possibly use to illustrate these things and to help you remember them, like y equals x and y equals negative x. However, the dance moves for y equals 1 over x are for only advanced dancers. So you can give it a try, but here's the move you'd need for 1 over x. Here's y equals negative x, and here's y equals negative 1 over x. I'll leave it up to your imagination to figure out a dance move for 1 over x squared and a dance move for negative 1 over x squared. But go ahead and have a little fun with those things if you need to get up and stretch and move around a little bit. But you might be saying at this point, hey, I thought we started with rational functions and we were going to learn about the graphs of rational functions. So far, all we've looked at is the graph of these very simple inverse power functions. What about the graphs of a polynomial over a polynomial, not just a constant over x to a power? What happens when these things get more complicated?